Okay, so your written test number 2 has been released for its result yesterday. If you want to go over with me the question and answers, just reach out as ever. Your lab number 5, that'll be the last lab. It has been released, and notice that I pushed the deadline somehow to the last day for you to turn in the fall work. So you definitely got enough time. I really want to draw your attention, given how deep we really discuss the inheritance issues, in the lecture. You will be able to do some self-study for abstract classes and interfaces. I made available all the resources to you. I got slides, I got notes, I got lecture videos. You can choose which one you want. Videos are optional. If you can simply gain the information to learn about the topics using slides, that's absolutely fine. But if you want to have some detailed walkthrough with me about the subjects, you can also go over the video. It's worth your time. All right. Your programming test number 3 will be tomorrow. That'll be the last programming test. Make sure you come in time. If I can start the test earlier to give you extra time, I'll definitely do so. Just arrive early. Okay. And then, just clarification, it will not be covered in this test. You don't need to worry about equals method to override it in your own classes. You also don't have to worry about aggregation composition, copy constructor. It's not covered. I'll save that for the exam. Okay? All right, and then bonus opportunity, just about a formal course evaluation. You guys have been very, very supportive. I don't see anything yet, but the response rate has been going well. But anyway, it's completely optional. If you are interested, feel free. All right. All right. Guys, any question about the course for me to clarify? All right. If no, let's now do a recap, and then we'll continue with our discussion about inheritance. Okay. So let's see where we were. So last time we actually started with the rules of substitution. That's basically how we started, right? And for the rule of substitution, I want to just remind you about this particular diagram over here. You want to have a very clear idea what the rule is about. Basically, given a class somewhere in the middle of some inheritance hierarchy, so there are 3 cases for you to worry about. Number 1, it would be okay to substitute static type A by any of its descendant classes because its descendants can fulfill its expectation. So you can see that the keyword expectation is really how we gain the intuition about how to understand every rule, including the variable substitution and also typecasting. And we're going to do even more today. Everything is about expectation. And that's about case number 1. So that'll be the only case where it is safe to do substitution. And case number 2, if you try to substitute static type A by one of its parents' ancestor classes, it will be unsafe, right? We spoke about it. Also, it will be unsafe to really substitute A by a class that's neither ancestor nor descendants because they cannot fulfill expectation, right? So I think this diagram here is the most important one to conclude from last Thursday. And of course, we did the various examples. You can go over them and let me know if you got any trouble understanding them. And then we go ahead. Okay, this is also valuable. When you try to trace your object at the runtime, sometimes it might be worthwhile to put the static type besides that. Not necessarily every time you will see what you need. So in the final exam, I will not really require you to draw some diagram for me to grade. Not really. But of course, since there will be quite a bit of question about tracing, so I think sometimes it will be worth your time to really put the static type aside. I'll speak more about your final exam either on Thursday or maybe next Tuesday, so you can also get prepared for that. All right, so we talk about dynamic type. So there are 2 ways for you to change the dynamic type. Either you can reassign the variable to some new expression, in which case this will be the new dynamic type. That's approach number 1. Approach number 2, if you simply try to reassign variables, let me show to you here. For example, you see Jin. First of all, it's assigned to RS. Later on, it's reassigned to NRS. So the dynamic type for Jim is just going to keep changing to here and then to here, right? It depends where you are. And dynamic binding tells you that whenever you try to call a method over here, the version that's going to be called depends on the dynamic type, right? And we're going to learn about an operator today that's to do with checking dynamic type, right? We'll also get there. All right, after this, we define polymorphism and dynamic binding. So think about polymorphism is once you declare a variable of certain static type, what would be the range of possible dynamic types that can fulfill the expectation of its static type? That's about polymorphism. Dynamic binding tells you, given that the variable substitution compiles at a runtime, which version of the method that's going to be called depends on the dynamic type for the context objects, either here or here. They might be different. If there are different versions, you might call different versions. Sorry, if there are different dynamic types, you might call different versions of the method. All right, so I think these two are also very important to really take away from this course. All right, we talk about cast, and we spoke about this A+ challenge. Just remember that, of course, we wouldn't dive into the theoretical detail. It's really for your general knowledge. For any programming compiler, it is simply undecidable or simply not possible for any compiler to keep track of the dynamic type for all the variables in general. It's simply not doable. So that's why we have to somehow do some workaround. So the workaround will be you gotta cast your variable into a particular type, which effectively creates an alias that's going to have the static type that you might need for later use. Right? You can also follow through the notes for that. And we'll talk about you can give a name to the alias that's created by the typecast, or you can simply do something like this. You can try to cast the variable here, but don't forget you should always put parentheses around. Otherwise, you're going to run into some errors, which I also tried to explain last time. Okay. All right, and then we just talk about compilable cast. So under what circumstances are your typecast compilable? We're not even talking about runtime, just talking about compilation time. So the idea will be very easy. Given that you got static type over here, I'm not even talking about dynamic type because I'm only considering for compilation. Given the static type over here, I can either do upward casting to one of its ancestor, it's compilable. Or I can do downward casting to one of its descendants over here, right? So this is why I got a later diagram over here, right? If you look at this diagram here, I would say maybe looking at the final version there could be slightly messy, I agree, but it's not unavoidable. It might be your best interest to maybe rewatch just this part of how I developed this diagram over here. You want to understand that given a particular variable declaration and with some dynamic type at the moment. So you can see Android is a static type. Samsung is a dynamic type. Given that, we can somehow categorize the whole inheritance hierarchy into different categories. Okay. So we talk about number one, compilable cast. Either you can do, so it's all with respect to the static type. You can either do upward casting or you can do downward casting. So all the ancestor and descendants, if you try to cast to them, either upward or downward, is compilable. All right, that's category number one. Category number two, any classes that's neither ancestor nor descendants of the static type, if you try to cast to them, it does not even compile. All right, that's category number two. Category number three, given that it compiles, let's now talk about what's going to happen if we try to execute the code. If I try to execute the code, then I will have to consider dynamic type. All right, now we'll talk about the runtime. Either the dynamic type simply cannot fulfill the expectation of the cast type. For example, if I try to cast Android into Huawei over here, it's a compilable cast because it's downward casting. But the dynamic type Samsung simply cannot fulfill Huawei. So we're going to run into the so-called class cast exception. Okay, let's make it more general. Under what circumstances can we have class cast exception? All right, the idea would be if you try to cast downwards into a class which cannot be fulfilled for its expectation by the dynamic type, then it will be class cast exception. Otherwise, there will not be any class cast exception, right? So of course, you can review just everything I said about this notes last time. Now I'm just doing some quick recap. All right, guys, any question from last time? We're just missing one little piece in the puzzle. If class cast exception is actually possible if we are being, for example, careless, maybe somehow I'm losing track, even myself. I forgot about what should be the current dynamic type over here. somehow I downcast into Huawei. So I don't really want to get into run like a class cast exception. Is there a way for me as a programmer to buy some insurance, to have some safety net to check? Yes, there is. So that's something I'm going to start with today as well. All right, if no further question, I want to refer you to some document here. So if you go to slide 66, so there's a PDF over here. If you open it, you will see that there's a short notes over here, only about 5 pages, right? So I think this one here also summarizes very nicely about static type, dynamic type, and typecast. All right, so that one will be also for your study purpose. I'll leave that to you. If there's any part you don't really understand, reach out to me. Okay, before we talk about how to use the operator to check the dynamic type, why don't we do one exercise together just to reaffirm everything? This could be potentially a format for final exam, so I think it'll be worth everybody's time to do it together. Now, step number 1, if you can grab a piece of paper or whatever, given the class declaration over here, are you able to draw the inheritance hierarchy to start with? Number 1. Okay, take a 1 minute or 2 to draw the diagram. And once you have drawn the diagram, think about line number 1 and line number 2. Okay? A simple question. Do line number 1 and line number 2 together compile? That's the question I'm asking. Yeah, take 1 minute or 2, and then we'll go over the answer together. And there will be some follow-up exercise to this as well. Some interesting phenomenon to observe. And of course, here I'm only giving you like 4 classes over here. You just have to be able to draw, when I increase the number of classes, which shouldn't be too bad, right? Once you know how to do in a small number, you should be able to do a bigger number. Okay. And my tip would be, let's say if you're given some questions related to something like this in the exam, you definitely want to make sure you draw the diagram accurately based on the Java declarations over here. You want to double check or even triple check, because usually there might be multiple parts of question that follow. So if you draw the diagram wrong, then all the answer is going to be wrong, right? Double check. That'll be the most important tip. Alrighty, hopefully everybody somehow get an idea, right? All right, why don't we check your answer? Should look something like this, right? You can see that we start with A, B extends A, and then C extends B, and then D extends A, right? That's a diagram. And then we want to judge to see whether line number 1 and line number 2 should compile. Let's just go over that. First of all, in order for this particular variable assignment to really compile, we want to make sure the dynamic type C can fulfill the expectation of the static type B. C can fulfill B because it's descending class, right? That one, check. What about line number 2? Is this cast compilable? All you gotta ask yourself will be, is it a downward or upward cast? Neither, right? You can see B has a static type B over here. I'm trying to cast B into its sibling, neither to the ancestor nor to the descendants. So it does not compile. All right, that's number 1 to see, right? Does not compile. The cast is not compilable because neither upward nor downward. Neither upward to some ancestor nor downward to some descendants. That'll be the more complete answer. Okay, so now let me show you something here. I can somehow trick the compiler to make it work, compilation-wise. So let's say I got the left-hand side. D, and D, right? That's how I started with. That one doesn't change. And then I want to say the following. Okay, you see what I'm doing here? Try to see if you can follow the diagram to see what I'm doing here. All right? What I'm doing here is, I know that I cannot do a single step for cast that's neither casting to ancestor nor casting to descendants, but I can split that into two individual steps. What I'm doing here is, step number one, I try to cast from B to A. Absolutely fine. And once I got that one there, that one has a static type A. Now I can downcast from A to B, so to D here. So individually, I'm doing an upward cast or downward cast. That's absolutely fine for the compiler. So what does this tell us? That tells us, basically, you can cast from any class to any other class in Java. How is that possible? Can anybody imagine? Because here you can see I can simply cast B to the top of the hierarchy and then go down to where I want to. What about just in general? How can I cast from string into point v2? How do I do that? Aha, exactly. All right. So I'll just write it down for your reference. I'm just telling you that's possible. I'm not saying that you should do it, right? That's a bad practice to do. I'm going to tell you the consequence, right? So for example, if you want to cast, let's say, if I have some object over here, let's say statically it's a string. What I can do is, first of all, I'm going to upcast that into objects. And then I'm going to downcast that into whatever I like. I can say point v2. I can do this because object is the ancestor for any class in Java by definition. And also, any class is also the descendants of objects by definition. I can just do that. All right? But it's very bad. All right? The price you may have to pay will be class cast exception. All right? So this one here, it will compile. Okay? So you can think about this one here is doing some upward casting. And then the second one there will be downward casting. But if you try to execute this piece of code, you got to run into class cast exception. And this will be also a very nice point to review why we're going to run into class cast exception. To really see why, you have to see the dynamic type, since we talk about runtime error. Let's just see where we are. You can see B doesn't change its static type. It's always the B over here, right? That's a static type. And the dynamic type, we also didn't reassign, so it also remains the same. It's here. All right, so that's the dynamic type. So this one is a static type, and this one here is the dynamic type. All right. And then what we are trying to do is we manage to cast that into D, ultimately cast. All right. Think about this is the ultimate answer we got. This is the ultimate cast type. And class cast exception is very easy to tell whether that's going to happen or not. You just want to ask yourself, can the dynamic type over here fulfill the expectation of the cast type? No, it cannot, right? Because the dynamic type C cannot fulfill the expectation of the cast type D. Or to be even more precise, cannot fulfill because it's not a descendant of. So this is a little nice example there that really put everything together, right? We got variable substitution here. We also got typecast. We got compilable cast. Also, we got upward, downwards. Also, we got class cast exception, right? Everything. All right, any question about this question here? Yes. Sure. The class cast exception, by definition, is very easy, as follows. Let's say, well, when can class cast exception occur? it can only occur when you try to do a cast. For example, here, right? Okay. When you try to do a cast over here, and the runtime at Java is going to check, can the dynamic type for this particular object is B, which is pointing to some C objects, right? It's basically asking, because after the cast, presumably you're going to use the alias as if it's like a D objects. So all the expectation is going to be imposed based on D. So we better make sure the actual objects can actually fulfill whatever that's imposed on D. If it cannot fulfill, then it should be a class cast exception. Okay. So normally, if you look at Java tutorial, they don't really explain this much detail. That's a shame. But now you guys really want to understand exactly what's happening here. Whenever you want to cast your object into some cast type, it will run into a class cast exception if the dynamic object there cannot fulfill the cast type, meaning that the dynamic object there, C, is not a descendant of the cast type D, right? So these are the complete reasoning behind. All right. Think about it. I don't mind if you ask me again, maybe later in the lecture or in the review session, because these really take some time to really appreciate how important it is. Yeah. Yes, yes. So to be more precise, if you look at this example here, again, if you only have line number 2, it's not going to compile, right? Because it's casting neither to ancestor nor descendants. But with these two intermediate casts over here, it will compile. But if you try to execute it at a runtime, you're going to run into class cast exception. Yeah. Okay. And why don't you guys try, once you go back home today, why don't you try to cast string maybe into, I don't know, vaccine. It can work compilation-wise, but it's not going to run without the class cast exception, right? All right, if no further questions, let's now move on. Okay. Okay, so we are done with slide number 67. And then let's now talk about a very important operator. It's called instance of operator. And the way it works, you just have to somehow remember it's working by expectation again. All right? Instance of is actually, okay, let me say this. Let me give you some like a takeaway page right away. Very simple. All right? So you're basically going to have instance of is like a binary operator. So you got instance of. Okay, it's a binary operator, meaning that you're going to have operand number 1 and operand number 2. All right? And it's a Boolean operator. It returns a Boolean. Meaning that true or false. Okay? And typically, this over here should be a class name. And the left-hand side over here typically should be an expression. And the expression usually should denote some objects. Some object could be a reference variable, or it could be some reference variable dot get something. So as long as it's some object value, then it could be the left-hand side. That's typically the case. All right, the definition is very simple. Okay, let me say this is x, this is y. All right, it goes like this. It's going to return true if x dynamic type can fulfill the expectations of y. That's the definition. And when you say x can fulfill the expectation, that means x should be a descendant of y. Agree? So there are several ways for you to interpret this. Can fulfill. So it can be either because x is a descendant of y. You know, let me be more precise. It's either that x dynamic type is descendants of y. Or alternatively, y is an ancestor. Either way works, but visually speaking, all right, you can think about x is really pointing to some objects over here. That's the expression. And then this one here, oh, how about this? And this one here, let's say this is a dynamic type for x, right? That's how we visualize it. And then we are saying that in the inheritance hierarchy, this particular dynamic type should be somehow a descendant class of y. If that visualization makes sense to you, right? It's a visual. X itself is not a type. X itself is just an expression, which is pointing to some objects of certain dynamic type. And that dynamic type should be able to fulfill the expectation of class y. So that's why I put that as a descending class, right? You kind of follow the ancestor path all the way to somewhere in the inheritance hierarchy. That's how you visualize it. Okay, so that's the rule. And then we just gotta do some examples together, right? One more thing to say. And of course, it will be false otherwise. If he returns true, means we can cast x to y. All right? And we can write it as y is going to be the class that we want to cast into, and then we can simply cast x to y. And it's guaranteed there will be no class cast exception. Class cast exception free. Okay, let's do a recap and then we can move on to some example. The instance of operator, by the way, it's a single word, instance of, there's no space. Okay, instance of. It's a binary operator. You got some object expression on the left-hand side. You got some class name on the right-hand side. And it returns a Boolean, true or false. It returns true if the dynamic type of the object that's being pointed to by x can fulfill the expectation of y, meaning that this dynamic type should be a descendant class of y. Or alternatively, this class here should be its ancestor. And if you're able to do this check and get, well, you can say, for example, if this particular expression returns true for me, I can now do some cast over here. I can now cast x to y without the worry about class cast exception, because it's guaranteed x's dynamic type can fulfill the expectation of y. All right? That's all you need to know about instance of. Now we just need to do examples. Lots of examples. Let's do the simple ones. All right, let's see here. Let's say we have Jin over here. You can see we got static type students over here. We got dynamic type non-resident students over here. And if we simply try to do, for example, this line over here, for example, only look at this line, line number 3. Look at that first. This line alone is going to compile. Agree? Because you're basically casting from Jin, which is static type students, down to resident student. It's a downward casting. Agree? So that will compile. So resident student here, resident student over here. This is downward casting. Let's say we don't have the instance of check. Let's say we don't. If you try to execute this line here directly after line number 1, you're going to run into class cast exception, because dynamic type here cannot fulfill the expectation of the cast type for the reason that we mentioned earlier today, right? All right. So what's the use of instance of? The instance of, as I said, is going to buy you some insurance. Every time before you try to do some typecast, if you want to be sure you're free from a class cast exception, you can say, can the dynamic type of Jin really fulfill the type I want to cast into? So you simply put Jin instance of resident students. I'm going to write it down for just one time, okay? Because for later example, we follow exactly the same pattern of reasoning. So if you, let me just highlight this line here, just this line here. Okay, this one here is a Boolean expression. It's basically asking, can the dynamic type of Jin, and we know that it is non-resident students, fulfill the expectation of the cast type resident students? That's the question. The answer is no. So it's going to return false. No. So that means the instance of will return what evaluates false. And the fact that evaluated false, you're going to evaluate false for the if branch, so you're going to bypass here. You never get into the point where you might get class cast exception. All right? Do you really have to do the instance of check for every class cast you do? Not necessarily. I would say only the points where you're not exactly sure what the dynamic type is for the object at this point. You will see exactly what I mean when you do the exercises. All right? Not necessarily just in this course. Maybe when you get to 2101, the data structure course, you might find the instance of operator also useful. All right, guys, any question here? If you understand this example here, that's great. We're just going to bombard you with more examples, right? It's really the same principle here. All right, let's now do more. Okay, this one here, very similar. Okay, let's say this. We have a variable smartphone over here, static type. And we got a dynamic type, Galaxy S21 Plus dynamic type. All right. And then we want to know whether or not we can cast a phone which has the dynamic type into iPhone 13 Pro. All right, you got to talk about two things. Number one, does it compile? It compiles because from smartphone down to iPhone 13 Pro is a downward casting. All right, number one. Number two, if it compiles, if I execute this line directly without any check, am I going to run into class cast exception? Yes, because iPhone 13 Pro, the cast type is here. Can the dynamic type here fulfill the expectation of it? Not really. Neither it's not. This is not the descendants of that, so it's not good. So that's why it simply try to do this instance of check. Once this, if this can evaluate it true, that means it will be safe to do the cast. All right. Let me write a slightly different comments over here. So this expression here, using instance of, it will be true. That simply implies safe to write the typecast, which will be iPhone 13 Pro, and then we got a phone. Safe, which means without any class cast exception. All right. All right, any question here? All right, sounds good. Let's do more. Let me summarize that a little bit, just a little bit more general, but everything has been said already. Right? This page here, I'll try to leave it as clean as possible, but it's also nice to visualize the rule more abstractly. Let's now consider you got some static type for objects, which is A. You got some dynamic type, which is B. Right? B must be a descendant class of A in order to be substitutable. And then you kind of intend to do some typecast, which is question mark. Now I'm basically putting this as open-ended. I'm asking basically what will be the range of cast type you can put over here such that you're not going to run into class cast exception. All right? And of course, before the cast, you can also try OBJ instance of that particular cast type. Right? It's like I say, before I try to cast a phone into iPhone 13 Pro, I try to make sure a phone is an instance of iPhone 13 Pro. Similar, right? I want to cast into question mark. So before that, I want to make sure OBJ that I want to cast into is an instance of question mark. All right. For line number 1 over here, it will compile if B can fulfill expectation of A. We said about it on Thursday last week. And also for number 3 over here, it will compile if we do either upward casting or downward casting. Meaning that we either try to do upward casting to some ancestor of A or downward casting to some descendants of A. Right? That's about compilation. Right? That's line number 3. Now, let's talk about line number 2. That's the most interesting bit. All right? If I try to say OBJ, which currently has the dynamic type B, what class can I put here to make the evaluation of instance of true? Okay, question mark over here. What can this be? To make the instance of evaluate to true. All right, that's a critical question over here. All right. Basically, any class that can be fulfilled by the dynamic type of B, dynamic type B, that should be okay. All right. Yeah, think about line number 2 here, right? So this will be the question over here. And the answer will be any class whose expectation can be fulfilled by the dynamic type B. So you really want to look at the answer and also question over here, right? So here is a question about what class can I put over here to make the instance of pass? The answer will be, since I'm checking to see whether the dynamic type of OBJ, which is B, can fulfill this. If that fulfill, then it will return true. So all the classes that can be fulfilled by B should be okay, which will be B, its parents, its grandparents, basically all the ancestors along the way. All right? So this part over here, I'm just going to, here. How about this one here? Okay, this will be the classes along the ancestor. So here, the question mark can be any of B's ancestor to make the instance of evaluate to true. All right, so that's the conclusion. Any of these ancestor to make it true. I know it's abstract, but based on the example there, I think it's not too bad. It takes some time. All right. All right, any question here before we do more examples? All right, good. Let's now do more examples then. Right, let's now talk about instance of, right? I got a series of instance of. All I want from you guys will be either true or false. But before that, let's be fair. Let's now do some annotation here. I got my phone over here. I want to check my phone instance of some class name. I got Android, I got Samsung, etc. All right. Before that, let's do some annotation. My phone has the smartphone static type. Also, my phone has the dynamic type Samsung. You got everything you need to answer the question. All right. My phone instance of Android, true or false? True, because Samsung can fulfill Android. All right. My phone instance of Samsung. No question about it. That's easy, right? Itself. My phone instance of Galaxy S21. False, because dynamic type here cannot fulfill Galaxy S21. My phone instance of iOS. False, because this one here is not an ancestor. All right, Samsung just cannot fulfill that. Finally, My phone instance of iPhone 13 Pro. Also false, right? Of course, the names over here for the classes can help you quite a bit because it doesn't make sense if I tell you that Samsung can fulfill iOS. It simply doesn't make any real life sense. So in the exam, you may not see exactly like a meaningful names. You might just see symbols, A, B, C, D. So I really want to test you if you really understand the rules. But we can start with something easy to start with. Question. Yeah, so CAS will be another, will be the next step. Yeah, for example, the fact that, okay, so this will be good, good, and also not good, not good, not good. When I say green check, that means true, right? Cross check, that means false. For example, the fact that you got true from this expression here, if you say if this is the case, and the next step will be you can cast my phone into Android. That's definitely the next step you can do. On the other hand, if you wrap around this instance of inside the if then else, right? If you say if this one here, I'm gonna do the cast. Now it can save you from the class cast exception because this one here is gonna return false, which will disallow you to really even go to the branch over here, right? Yeah, false tells you shouldn't really try to cast it. Yeah. So of course, but let's say if you got if over here, but somehow you still put a cast outside the if, nobody can save you, right? You gotta put it inside the branch. Yeah. Okay, any question here? Good. Okay, more. Oh, actually this one, that's exactly what you just asked. I forgot, actually I have some notes for that. So you can see that because I know that this one here, by the way guys, this example here is just the same as the previous page, just the same, right? I kind of built it up. I forgot. That's how I designed the slides. Because I know that this guy over here is going to return true. Green means true. On the other hand, these two will be returning false. What does that mean at the runtime? At the runtime, because this is returning true, so I will be able to execute this typecast without any class cast exception. On the other hand, because this instance of is going to return false, I will be able to bypass this typecast, right? If I didn't have this line over here, I try to execute this right away. In that way, Samsung cannot fulfill S21 Plus. You're going to get class cast exception. So this really shows you the value of having some instance of check beforehand. All right? And this one's similar. So instance of is not too bad, right? You just have to make sure you kind of understand it from the perspective of expectation, right? Ancestor, descendants, expectation, that's really what you need to really understand the whole thing about inheritance. Yes? Yeah, for instance of, you can definitely feel free to actually use it in lab 4 or even tomorrow's test. Even without instance of, I think in lab number 4, if you simply use a get class method that we used earlier, that's okay. It's not ideal, but now you learned about the ideal solution, right? So for tomorrow's test, I don't mind if you use the instance of or the get class method, whichever that works for you. But when you guys look at the solution for lab number 4, I did use the instance of, which is pretty straightforward to use. So feel free. All right. Oh, question. Go ahead. Uh-huh. Say it again, sorry. Oh, I see. You simply return. Interesting. I wouldn't disallow that for tomorrow's test, but it's not ideal. Because somehow you kind of are doing what the instance of what get class can do for you. It's like a duplicating the efforts. So I would suggest maybe try to use instance of. That'll be the most ideal. But for tomorrow, if you can work around it, I don't mind. It's a test, right? So we wouldn't check. Alrighty. Okay. All right, so I think 1, 2, 3, 4, 5. Okay. Okay. How about we do 5 more examples? They're pretty quick. It's just to show you a little bit more about typecasting, everything put together, right? Nothing new. Let's finish that, and then we'll do some brief break. All right. All right, let's see what this example is about. This one here, let's start with, it kind of shows to you about what's going to happen at the compile time versus runtime. And for now, let's talk about compile time. It's a review about expectation, okay? So we have SP smartphone. It has the static type smartphone over here. So this one basically tells you if you want to use SP as the context object, what will be the range of methods you can call, all right? So now, can you call sp.dial? Yes, it's here. sp.facetime? No, because FaceTime is here outside the expectation for smartphone. Even though dynamically it's an iPhone 13 Pro. Doesn't matter. We talk about compilation. Similarly, sp.quicktake, it is available to iPhone 13 Pro, but static type wouldn't allow it. All right. So the conclusion is, even if the dynamic type can support FaceTime and quicktake, but we talk about compilation. All right. So what's going to happen is this one compiles, but these two simply does not compile. This one shows you how it shows you that the compiler doesn't keep track of dynamic type, which means we need typecast. All right. So the next phase will be similar idea. So let's say we got iPhone 13 Pro. Let me put it here just as a context, okay? Given that smartphone itself is too high in the hierarchy, why don't I lower that a bit? All right. So what I do is I change the static type to be iOS, right? So iOS is going to be, oh, sorry, wrong color. iOS over here. Dynamic type is still iPhone 13 Pro, which can still fulfill iOS, which is fine. Now, have we increased the expectation? We have, because it's now lower, right? So you can certainly do dial, you can do FaceTime, which is declared over here, but you still cannot do quicktake because it's only available over here. All right? Right? Next one. All right, so now that's the final one. If I try to make the static type just the same as dynamic type, this one here and this one here, they just happen to be the same. You can think about iPhone 13 Pro and also dynamic type just the same. In that way, whether you can compile depends on the static type. In that way, you got dial, FaceTime, and quicktake, all of them, right? All right. 1, 2, 3. Okay, that one's easy. Let's now put some typecast into the context, especially anonymous cast, which we learned last Thursday. Let's now see more example. We know that, let's say this. SP has smartphone over here. Just by SP itself, we can only call dial. We cannot call FaceTime. We cannot call quicktake. But let's now do some casting. What I'm doing is SP, I'm doing some downward casting to iPhone 13 Pro. So it's a downward casting, all right? Downward cast. So you can think about this expression over here is an alias with the static type iPhone 13 Pro. Right? That's all we learned about cast. Once you have done this, can I do dial? For sure. Can I do FaceTime? Of course, iPhone 13 Pro, of course, will support FaceTime. Can I do quicktake? Of course you can. You can see, right, that with the typecast, you're able to actually increase the expectation by creating some alias. And question for you, are we going to run into class cast exception? How can you have class cast exception? You have class cast exception if the dynamic type, which is also iPhone 13 Pro, when the dynamic type cannot fulfill the cast type, which is not the case. Dynamic type for SP is iPhone 13 Pro. Can it fulfill itself? Of course it can. So no class cast exception. All right. If you haven't really developed such fluency, that's okay because you're just learning. But it takes some time, but you want to make sure it's quick, right? Before the exam. Okay, so here, also make a note over here, no class cast exception. No class cast exception. Okay, final one before we take a short break. And this one here, okay, just another example for anonymous cast. You can take a look at here. So we got 2030, that's fine. We got student S. You can see S has the static type students, right? I put it as part of the visualization. That's a static type. The dynamic type is resident students over here, okay? And then my intention is to somehow cast the S into resident students. I should be able to do it. But to be 100% safe, I can also have some instance of check over here. I'm asking, can the dynamic type of S, which is resident students, fulfill resident student itself? In this case, yes. So this is going to give me true, in which case I'm going to do the cast. And here I'm just showing to you, I can just do the typecast over here and then do the set premium rates. Okay? That's just another example for you to see. So you can think about this part over here before the dot. So this is an alias with the static type resident students. So that's why you can call set premium rates. Okay. Similarly, if you try this one here and say get tuition, it's going to call the version that's defined in the dynamic type resident students. Okay. All right, any question? We are now done with basically all the, you say, theory part or maybe definition part for typecast. And it's not too bad, I hope. Okay, we can take a short break, but let me just tell you what we're going to talk about after the break. We are going to somehow link what we learned about inheritance so far with call by value. That's going to be exciting. All right, so why don't we take a short break now and taking attendance, okay? Okay, so let's just briefly go back to the slides. I think we have covered basically everything until, let me just tell you where you can also get started with your study. Of course, this is not covered in any further written test, but it will be covered in the exam. I'll definitely talk about your exam format and some expectation maybe Thursday or next Tuesday. Okay, I'll talk about it. So, yeah. Okay, instance of, we spoke about it. And then the series of examples, you can also give a try. And we got all the way to slide. I didn't skip anything. Everything has been covered when we go over the example, right? 76 so far, all right? We should be able to go over a few more, all right? So we can save some time for Thursday. I'm hoping that on Thursday we can definitely finish off the inheritance and we can do the last topic. We can start with it, recursion. All right, so that'll be the idea. Okay, so now we're going to put basically polymorphism, something about variable substitution, together with call by value together. Okay, it's not too bad, I can tell you. Once I visualize what you should really make the connection to, is basically go back to where we are about the rules. Okay, let's now take a look at this class definition. Let's say we have a new class over here, student management system. If you recall back in maybe a few lectures ago, maybe 3 or 4 classes ago, I said you want to consider 2 versions of the student management system. One version will be, let's say we don't have any inheritance, in which case we need to have multiple arrays in the class. And now with inheritance, we need just a single array. And we want to study exactly how polymorphism will work. I will do the exact comparison and contrast maybe on Thursday. But today, let's focus on the more technical issue about how things will compile and how things might go wrong at the runtime. All right, let's say this. We got student management system, and you can now make some connection to your lab number 4. How about this? Imagine that this class is maybe your channel. Okay, this here can be an array of follower, which can be either subscriber or monitor, something like that. Okay, just make that connection in your mind. All right, let's say we got a student array SS. And then Let's now talk about some important issue here. Okay. For this class over here, as soon as you declare this particular variable, you can see the attributes and also student array. We know that the static type for SS is student array. But what's going to be more valuable is what's the static type for SS at index 0, index 1, all the way to the last elements. That's the critical question. Static type. Whatever it's declared to be, student here. Agree? If I tell you that SS simply stores a collection of students, what should be the individual slot for its static type? Of course, it should be individually a students. Right? Makes sense. So that's the number one thing you want to observe right away. Students. All right. And let's now consider one of the methods here. Let's say I have a method here, mutator. It's called add_rs. I intend to add a resident students. So that's why I actually put the resident students over here as the parameter type. So you can think about the resident student over here is the static type for parameter rs. Static type of parameter rs. And then I want to ask you guys one question. Consider this variable assignment over here. Does it compile? If so, why? If not, why not? You already got all the information you need. All you got to do is to check to see whether this variable substitution or assignments is valid. That's all you got to check. Right? This one here. Anyone want to share? If no, I can tell you the answer. Yeah, go ahead. Yes, I agree. So I would say yes, it's definitely right to say resident students is a descendant of students, but let's be more complete. Let's say this is a final exam question. All right. So all you got to check will be RS over here was declared to be resident students. We know that its static type is resident students. On the other hand, we learned earlier for SS as some index C, right? The previous question. Index C can be 0, can be 1, can be all the way to the length -1. All right? So this one here has the static type students. And whether or not this should be valid or compilable depends on whether or not RS is a descendant of students. It is. All right? So this one here compiles. You can do the similar reasoning for this one here and this one here. All of them compile. Any question? Nothing really new, really. All you gotta, the only thing I would say I didn't really mention explicitly was how do you figure out the static type for parameter? Well, whatever type is declared to be. No surprise. All right. So now here comes the critical thing. All right. Let's read the question together. Under what circumstances can this particular method call? Let's say SMS is an object of type student management system. I want to invoke add_rs over here, which has a static parameter type resident students. I'm asking what kind of objects can I pass over here to make this method call compilable? Specifically, what should be the type of the argument that's allowed to make this method call compilable? That's the question. That's a new bit we have to learn in the final part of this lecture today. It might sound very tough, like it's like out of nowhere. Suddenly, I'm asking you this question. Not really. Remember, I gave you a hint before the break. Call by value. All right. Let me remind you what call by value is. So here, I'm calling add_rs which is declared over here. And the way I make a connection between the method call and its declaration is by doing this. Okay, so I'm gonna do, how about this? Okay, what kind of connection can we make? Call by value. Implicitly, what kind of variable assignment are we doing when we talk about call by value? Are we trying to do RS is assigned to O, or we're doing O is assigned to RS? Or neither? Call by value, right? Guys, you got to review it. It's going to be covered pretty soon. RS, the parameter, is implicitly assigned to the argument O, right? This is the param. This is the arguments. And once you see variable assignment here, you should feel relief. We now go back to the rules that we are familiar about. All right? So in order for this method call to be valid, the implicit assignment that's happening because of call by value should be valid. For this implicit assignment to be valid, the static type for O should be descendant class of the static type of RS, which is resident students. That's the reasoning. All right? So the answer is this. The static type of arguments O should be a descendants of the static type of parameter, which is resident students. All right, this is a very important connection to make, right? We basically try to go back to the variable substitution rules that we are familiar with by using call by value, which we learned earlier. Okay? So that is to say, when we do the exercise on the next page, I'm going to give you various possibilities of making a method call over here. And we're going to answer whether or not that particular method call is going to compile. The way for you to judge is to see whether the static type over here, O, which will appear as the right-hand side in the call by value, that should be a descendant class of the static type of the parameter, in this case, resident students. All right? So I think that this part here is the most important part you want to maybe think about before Thursday. All right? Example. Let's now set up the context. Okay? Let's say we got S1, S2, S3, right? You can see all of them got static type students. They got different dynamic types. And we also got RS, NRS. Their static type and dynamic type just happen to be the same, which is okay too. So now we got S1, S2, S3, RS, NRS. We got different variables that may be passed as arguments to method call. Right? Let's see which one should be valid and which one should not be valid. All right? So you can see here we create SMS, which is a student management system. Okay, how about this? Why don't you guys take a look at this and think about? Okay, I got so many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why don't you guys take 1 minute? I think we have time. Take 1 minute to think about which one should compile and which one should not compile. And the hints will be call by value that I just mentioned in the previous page. And one thing to note, you can see here I'm calling add RS. Here I'm calling add students, right? Different method call, but following the same principle. Okay, just one more moment and see if anybody is already able to figure out the answer. All right. If no, Study a bit more. Hopefully you can do it by Thursday. Okay. Let's now try to block this one here. We talk about add RS. Add RS has the parameter static type resident students. That means any argument you pass over here should have its static type fulfilling this expectation because of call by value, right? Can S1 fulfill expectation for resident students? Can it or can it not? S1 declared to be students. Can student fulfill resident students? Not really. All right. How about S2? S2 happen to be a resident student though. Can it fulfill? You think yes? Seems like I misled you. That's good. No, you cannot. Because S2 was declared to be a student. It doesn't matter what the dynamic type is. All right, you got to look at the static type. All right. Also not good. Also, what about S3? Also not good because S3 statically is a student. Can students fulfill resident students? Not really. All right. So what I'm doing here is I have in my mind some implicit assignments over here. I'll just make it a bit thinner, which is about call by value. The call by value tells me that there would be an implicit assignment assigning RS by the arguments over here, question mark. And the question mark, I'm simply trying S1, S2, S3, and etc. All right? The next one, number 4. Can RS, resident students, fulfill resident students? Yes. All right? So that's the only one that compiles. And this one here, can NRS, non-resident students, fulfill resident students? No. All right? Hopefully that helps a bit, right? You're just getting a little bit better. All right, having slightly better understanding, can you try from number 6 to 10 now? Hopefully you have a better clue. I'm hoping. Apparently, now for 6 to 10, I'm talking about basically add students over here. Right? Whatever I put over here should have its static type being able to fulfill the students. Is S1 good? Yeah, S1 declared to be a student, so it can fulfill student. To be honest with you, this one is a very obvious answer because the parameter type I choose over here happen to be at the top of the hierarchy. What classes can fulfill the top? Every class. Because every class here in the hierarchy is the descendants of the top class over here. So that's why all these over here got their static type, all descendants of the students, which is over here. All right, that's the insight you want to get into. All right, this one tells you that when you got inheritance in the context, what kind of parameter do you want to really put over here? One extreme you can go would be, I can put the class over here as high as possible in the hierarchy so that I can allow as many arguments to be compilable to be passed over here. Or, on the other hand, I can put it to be very restrictive over here. That means in this case, only resident student itself can be passed as an argument, right? So these are the more advanced remarks that you want to revisit when you study for the exam. All right, so this one here, all these are good, all right? Because you want to think about, in this case, call by value. And it would be the ask students over here. And also the students over here, right? That's the connection you want to make over here. Okay, over here. The call by value Oh, actually, I got it already. And put it here. Sorry about it. Let me write it down again. So the call by value tell you that implicitly S is assigned to some question mark. And the question mark can be any of the argument that we put over here. All right? So we got two instances of call by value over here. All right, any question? All right. Okay, how about this? I think I can end the class earlier today. I already kind of covered more than I thought I would, which is good. And this page over here, I'm going to assign as an exercise for you to try. Okay, let me tell you what the exercise is about. It's important. Also, this will be the kind of a very nice example to summarize everything together. You want to think about the following. Okay, look at the page. When you look at piece of code 1, 2, and 3, ask yourself, why does this one here, and this one here not compile? Question number 1. Why does it not compile? Number 2, can adding this particular typecast over here make things compilable? Question number 2. Question number 3, after this is compilable, for case 1, 2, and 3, which one are we going to run into class cast exception? All right? That's the 3 questions you want to try before Thursday. I'll go over answer with you, but you better struggle to see where you really get stuck. You're going to get something similar in the exam. So why not try it now? All right, thank you so much. I'll see you in the lab tomorrow.